100,000 tons. That's heavier than the Eiffel Tower, and it floats. But here's what tours never show you. The ship doesn't start in the water. It starts as raw steel in a yard where welders build room-sized blocks, crane operators stack them like Lego, and nuclear techs install a reactor that'll run for decades without refueling. Then comes the hard part. They flood the dock, tow it out, and run trials that include setting off bombs next to the hull to prove it won't sink. This is the real build. No fluff, no tours, just the step-by-step process that turns metal into America's biggest moving weapon. Newport News Shipbuilding in Virginia is the only place in the country that does this. 3 dry docks, 15,000 workers, a gantry crane that can lift 900 tons at once, and every few years, they start from zero and build a nuclear aircraft carrier. Not assemble, not install, build. From cutting the first steel plate to the moment the Navy accepts delivery, the process takes about 7 years, and almost none of it happens the way you'd guess. Most people think a ship gets built like a car. Start at one end, work to the other, bolt things on as you go. Wrong. A carrier isn't built. It's grown in pieces, then combined. The yard fabricates small sections called units. Units get welded into blocks. Blocks get outfitted with pipes, cables, and equipment while they're still on land. Then blocks get joined into super lifts, chunks of ship so big they need their own structural analysis. Finally, the super lifts get lifted by crane into the dry dock and welded together to form the hull. It's modular construction at a scale that makes skyscrapers look simple. And here's the kicker. While one team is welding super lifts in the dock, another team is still building new blocks in the fabrication hall, and a third team is pulling cable through blocks that were installed 6 months ago. Everything happens in parallel. There's no assembly line. It's controlled chaos, and it only works because every trade, welders, pipe fitters, electricians, riggers, knows exactly when and where to move. Let's start at the beginning. Raw steel arrives in plates, some of them 30 feet long. Computer-controlled plasma cutters slice them into shapes. Those shapes get bent, heated, and formed into frames, bulkheads, and deck sections. Then the welding starts. A unit might be a single compartment. Walls, ceiling, floor, a hatch. Welders join the pieces, grind the seams, x-ray the joints to check for flaws. If it passes, the unit moves to the next station. If it doesn't, they cut it out and re-weld. No exceptions. Every weld on a nuclear carrier gets inspected, documented, and signed off. One bad joint 3 decks down could mean a flood in a machinery space during combat. So they don't skip steps. Once you have a handful of units, you weld them into a block. Now you've got a piece of ship maybe 40 feet long, 3 decks tall, and weighing a couple hundred tons. And here's where it gets smart. Before that block ever touches the dry dock, workers outfit it. They install piping for fire mains, fuel, cooling water. They pull electrical cables through conduits. They bolt in ventilation ducts, hatches, ladders, even light fixtures. Why? Because it's way easier to work on a block sitting on land than it is to crawl through a tight space deep inside a hull that's already welded together. This is called advanced outfitting, and it's the reason Ford-class carriers take less time to build than the old Nimitz-class ships. You're not sending a guy with a wrench into a dark bilge to run a pipe after the fact. You're doing 80% of the work before the block ever leaves the assembly hall. Now you've got dozens of outfitted blocks. Time to make super lifts. A super lift is what happens when you weld several blocks together on land to create an even bigger section, sometimes 500 tons, sometimes more. Picture a chunk of ship 5 stories tall and as long as a city bus. That's a super lift. The yard uses jigs and laser alignment to make sure everything lines up within a few millimeters, because once that thing gets craned into the dry dock and welded to the rest of the hull, you can't just shim it into place. The gantry crane, nicknamed Big Blue, does the heavy lifting. It straddles the dry dock on rails, picks up a super lift, rolls it into position, and lowers it onto the keel or onto a previously installed section. Riggers guide it with tag lines. Welders tack it in place. Then the real welding begins, joining the new piece to the growing hull with miles of weld bead that'll get inspected joint by joint. The sequence matters. Keel sections go in first, then the double bottom, which forms the lowest watertight spaces and adds structural strength. Then machinery spaces, where the reactors and turbines will live. Then the hangar bay, the island, the flight deck. Each superlift builds on the last, and each one brings the ship closer to looking like a ship instead of a steel jigsaw puzzle. And while all this is happening in the dock, other superlifts are being built in the yard, other blocks are being outfitted, and other units are being welded. It's a pipeline. Stop one stage and the whole thing jams. Keep it flowing and a 100,000-ton warship starts to take shape in front of your eyes. Now we get to the part most people never think about. How do you power a floating city? A Ford-class carrier has two A-1B nuclear reactors. Each one is about the size of a school bus, weighs hundreds of tons, and will run for 50 years without refueling. These aren't bolted in at the end. They go in during construction, deep inside the hull, surrounded by shielding and structural supports that get welded in as the ship grows around them. The reactor compartments are built with extra care, special welds, extra inspections. Navy nuclear inspectors watch every step. The reactors themselves arrive from the manufacturer already sealed. The yard doesn't crack them open. They lower them into place with the gantry crane, align them to within fractions of an inch, then weld the compartment closed around them. After that, workers route coolant pipes, steam lines, and backup systems. It's slow, precise, and absolutely critical. If the reactor doesn't work, the ship doesn't move. But raw power isn't enough. You need to turn that power into something useful. On a Nimitz-class carrier, steam from the reactors ran the catapults that launched jets off the deck. On a Ford-class, everything went electric. The Electromagnetic Aircraft Launch System, EMALS, uses linear induction motors to sling a 70,000-pound fighter from 0 to 150 miles per hour in 2 seconds. No steam, just magnets, capacitors, and software. Why the switch? Steam catapults are brutal. They slam the airframe with a violent jolt. They need constant maintenance, and they can't adjust the launch energy for different aircraft weights. EMALS is smoother, more efficient, and easier on both the plane and the pilots. It also takes up less space and weighs less, which means the flight deck can be redesigned for better aircraft flow. Same story with the arresting gear. The old system used hydraulic fluid and big drums to catch a landing jet's tailhook and drag it to a stop. The new advanced arresting gear, AAG, uses electric motors and rotary engines. It's programmable, it's gentler on the airframe, and it recovers faster between landings. Put EMALS and AAG together and you get higher sortie rates, more launches and recoveries per hour, which is the whole point of a carrier. Of course, none of this works without power distribution. A Ford-class carrier has about 1,000 miles of cable running through it, not an exaggeration. Electrical trunks as thick as your arm snake through passageways, branch into junction boxes, split into individual circuits that power everything from radar arrays to coffee pots. Every cable gets labeled, routed through fireproof conduit, tested for continuity, and logged in a database. Running cable is a trade unto itself. You're threading lines through tight spaces, around structural frames, through watertight bulkheads with special penetrators that maintain the seal. You're coordinating with pipe fitters so your conduit doesn't block their pipe runs. You're leaving access for future maintenance. And you're doing it while the ship is still under construction, so half the rooms don't have doors yet, and you're stepping over welding gear and scaffolding just to reach your work site. It's the same with data networks. A modern carrier has fiber optic backbones, redundant servers, classified and unclassified networks, links to satellites and other ships. All of that gets installed during the build. Terminations get tested, encryption modules get certified. By the time the ship leaves the yard, it's not just a hull with a reactor. It's a floating data center with enough bandwidth to run a small city. And here's the thing, all of this, reactors, EMALS, AAG, cables, networks, gets installed while the ship is still in the dock. Workers are outfitting compartments that don't even have a roof yet. They're pulling cable through spaces that'll be sealed behind panels in a few weeks. It's a race against the build schedule and every hour counts. Eventually, the ship is done enough to float. Not finished, just done enough. The yard starts flooding the dry dock. Seawater pours in through culverts at the bottom. Close enough to lift the ship and slam it back down. The goal is to find out if the design can survive a near miss from a torpedo or mine. If critical systems fail, the design gets modified before the next hull is built. Ford's shock trials happened in the summer of 2021. The ship took multiple blasts, it shook, it flexed. Some systems went offline temporarily, but the hull held, the reactors stayed safe, and damage control teams brought everything back online. The data from those tests fed directly into the construction of the next ship in the class, Kennedy, CVN-79, so it'll be tougher from day one. Shock trials aren't about proving the ship is smoother. The Yard applied the lessons. The contractors refined the design. The Navy adjusted the test protocols. It's still hard work, but it's not experimental anymore. That's the value of a ship class. You pay for the learning curve once, then you build the next ones faster and cheaper. Workforce retention is another big factor. Building carriers takes skills you can't teach in a classroom. You need welders who can read blueprints in 3 dimensions and lay perfect beads in tight overhead spaces. You need riggers who can calculate load angles and sling a 500-ton superlift without crushing someone. You need inspectors who know what a good weld sounds like when you tap it with a hammer. Those skills take years to develop. If the Yard loses experienced workers between ships, the next hull suffers.